Welcome! In this session, we'll dive into the problem add bold tag in string. Together, we'll explore the problem, break it down, and walk through the solution step by step. Let's get started. In this problem, we are tasked with taking a string S and an array of strings called words. The goal is to return a new version of the string S where any substring that matches one of the strings in words is wrapped in bold tags, specifically bn/b. If two or more matching substrings overlap, they should be merged and wrapped together within a single pair of bold tags. For example, if the input string is x is 123 and the words array contains abc and 123, the output string should look like babc/bxyz/b123/b. This ensures that the bold tags clearly highlight all matches from words in the string S. Additionally, the input constraints specify that S is a string of lowercase English letters, and the words array consists of lowercase strings as well, each with their own length and number limits. Ultimately, the output must be the modified string with the required bold tags applied correctly. Now, let's look at an example to illustrate this. If the input string S is x is 123 and the words array contains abc and 123, the output will be babc/bxyz/b123/b. Here's why: the substring abc in S matches the first word in the words array, so it is wrapped in bold tags. Similarly, the substring 123 matches another word in the array, so it is also enclosed in bold tags. Since these two substrings do not overlap, each one is wrapped in its own separate bold tags. This ensures that the output is a properly formatted string with all matching substrings highlighted, while the rest of the string remains unchanged. Let's consider another example where overlapping substrings come into play. If the input string S is AAP and the words array contains AAA, AB, and BC, the output will be BAAP/B greater than C. Here's how this works: the substrings AAA and AB overlap, as they both start at the same index but extend to different lengths. Additionally, BC overlaps with the end of AB. Because these matches overlap, we merge them into a single continuous range, which spans from index 0 to 5. This entire range is then wrapped in one pair of bold tags. The result is a single bold section that highlights all the overlapping matches, while the remaining C at the end of the string stays unwrapped. Now, consider a case where there are no matches. For example, if the input string S is ABCDF and the words array contains only the string GH, the output remains unchanged as ABCDF. This is because none of the substrings in S match any word in the words array. This demonstrates that if there are no matches, the input string is simply returned as is, without any modifications. Additionally, the constraints of this problem are important to note. The length of S can go up to 10,000, while the words array can contain up to 100 strings, each with a maximum length of 100 characters. These constraints mean that we need to consider efficient methods for processing the input, especially for large cases. Finally, let's review some edge cases to keep in mind. First, if there are no matches at all, as we saw in the previous example, the output will be identical to the input string. Second, when multiple substrings overlap completely, the entire range must be merged and wrapped in one pair of bold tags. For instance, if S is AAA and words contains AA and AAA, the output should be BAAA/B. Third, if matches are adjacent but not overlapping, they should still be merged into one bold section. For example, if S is ABCDF and words contains ABC and CDE, the output should be BABCDF/B. Lastly, because the input size can be large, it is crucial to ensure that the solution is efficient and can handle edge cases without exceeding time or space limits. To solve this problem, one of the first approaches we can consider is the brute force method. This involves iterating through every possible substring of the string S and checking if it matches any word in the given words list. Whenever a match is found, we keep track of the indices of the substring that should be highlighted with bold tags. Once all matches are identified, these marked indices are used to insert the BN/B tags, ensuring any overlapping ranges are merged beforehand. While this approach is simple and easy to understand, it comes with a significant drawback. The time complexity is O(n²*m), where n is the length of the string S and m is the total length of the words list, making it inefficient for larger inputs. Additionally, the space complexity is O(n), which accounts for storing the bold intervals. Despite its simplicity, this method becomes impractical when dealing with longer strings or extensive word lists due to the nested iterations required. To address the inefficiency of the brute force method, we can adopt an optimized sliding window approach that minimizes redundant comparisons. Instead of evaluating every substring, we directly locate matches using helper functions like find. The process begins by creating a Boolean array called bold, sized to match the length of the string s. This array is used to track which indices in the string should be bold. For each word in the words list, we iterate through the string s and use the find function to locate all occurrences of the word. Each time a match is found, we mark the corresponding indices in the bold array as true. Once all words have been processed, overlapping ranges of true values are merged, and the B tags are inserted accordingly. This approach reduces the time complexity to O and *m, where n is the length of s and m is the total length of the words list, while maintaining a space complexity of O, n, for the bold array. It's a significant improvement in efficiency, though managing the bold array and merging intervals introduces some overhead. For even greater efficiency, especially with larger inputs or extensive word lists, we can utilize a tree-based approach. A tree, or prefix tree, allows us to efficiently match words by organizing them in a hierarchical structure. The first step is to build a tree using all the words from the words list. Once the tree is constructed, we iterate through each index in the string s and attempt to match substrings by traversing the tree. Whenever a match is found, the corresponding indices are marked in a bold array. After all matches are identified, overlapping intervals in the bold array are merged, and the B tags are inserted. This method offers improved time complexity of O and *k, where k is the average length of the words in the list, as the tree eliminates redundant checks. However, the space complexity is higher, at O, k *m, due to the memory required for constructing and storing the tree. While this approach is highly efficient for large-scale inputs, its complexity can make implementation more challenging and less intuitive. Among these approaches, we chose the optimized sliding window method due to its balance of simplicity and efficiency. While the tree-based approach provides better scalability for very large inputs, it introduces additional implementation complexity that may not be necessary for smaller or moderately sized inputs. Compared to the brute force method, the sliding window approach is a substantial improvement, reducing the time complexity from O and squared *m to O and *m. Additionally, it avoids the overhead of building and traversing a tree, making it more straightforward to implement and maintain. By leveraging the bold array to track intervals and efficiently merging overlapping ranges, this method achieves an ideal balance between performance and readability. The key insight was recognizing that we could work directly with indices to handle overlapping intervals, simplifying the process without requiring advanced data structures like interval trees. This makes the sliding window approach both practical and effective for this problem. To solve the problem of adding bold tags to a string, we start by understanding the inputs and the desired output. The first input is a string s of length n, which represents the text we need to modify. The second input is a list of words that contains substrings we want to highlight by wrapping them in bold tags. The output is the string s, modified such that all substrings matching any word in words are enclosed in bold tags. Additionally, if any bolded regions overlap, they should be merged into a single bold region. To achieve this, the first step is to mark the indices of the string s that need to be bolded. We initialize a Boolean array called bold, of the same size as s, with all values set to false. This array will help us track which parts of the string should be bolded. Next, for each word in the list words, we look for all occurrences of that word in s. Using methods like find, we identify the starting index of each match and update the bold array to mark the corresponding range of indices as true. This ensures that all matching substrings are flagged for bolding, including cases where there are multiple or overlapping occurrences of a word. Once we have marked the relevant indices in the bold array, the next step is to merge any overlapping or contiguous regions. We do this by iterating through the bold array to identify ranges of true values. These ranges correspond to the segments of the string that need to be bolded. To track these regions, we use two pointers, start and end. When we encounter a true value, we check if it marks the beginning of a new bold region, for instance, when the previous value in the array was false. We then expand the end pointer until the true values stop, effectively capturing the entire bold region. Each identified range is stored as a pair of indices, start and end, in a list of ranges. With these ranges in hand, we proceed to construct the output string. For each range in the list, we insert the bold tags bn/b at the appropriate positions in the string. To make this process efficient, we use a string builder or a similar structure to avoid repeatedly modifying the string directly. This approach ensures that we can assemble the final output string without unnecessary operations, resulting in the desired format with minimal overhead. Now let's focus on some key insights that make this approach effective. First, by using the find method for substring matching, we ensure that the process of locating words in the string is efficient. This method allows us to quickly identify all occurrences of each word from the list words. Second, the Boolean bold array is a simple yet powerful structure for handling overlapping or adjacent matches. Because contiguous true values inherently represent merged regions, we don't need any additional logic to handle overlaps. Third, the use of a list of ranges simplifies the process of constructing the output string. Instead of modifying the string iteratively for each bold tag, we only insert tags at the start and end of the identified ranges. This reduces the complexity of string operations significantly. In terms of data structures, the bold array has a size of O, n, where n is the length of the string, while the list of ranges has a size of O, k, where k is the number of bold regions. Additionally, a string builder or equivalent structure is used to efficiently concatenate the final output string, ensuring that our solution is both time and space efficient. Analyzing the complexity of this solution, the time complexity primarily depends on the substring matching process and the construction of the output string. For each word in the list words, we may need to scan the entire string S, which takes O, n, time. Since there are m words in the list, the matching step has a worst-case complexity of O, n asterisk m. Constructing the output string involves iterating through the bold array and inserting tags at the identified ranges, which takes O, n, time. Therefore, the total time complexity is O, n asterisk m. For space complexity, the bold array requires O, n, space, and the list of ranges requires O, k, space, where k is the number of bold regions. Thus, the overall space complexity is O, n plus k. It's also essential to consider edge cases. If no words from the list are found in the string, the output remains unchanged. When the entire string is part of bolded substrings, the output wraps the entire string in bold tags. For nested or overlapping matches, our merging logic ensures that they are combined into a single bold region. Finally, we handle edge cases like empty inputs gracefully, returning the appropriate result without errors. Let's walk through an example to see how the algorithm works in practice. Suppose the input string S is abs is 123, and the list of words is ABC 123. First, we initialize the bold array with all values set to false, representing that no characters are bolded initially. Next, we process the word ABC and mark the indices corresponding to this substring in the bold array. The updated array becomes true, 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 false, 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 false. Then, we process the word 123 and mark its indices as well. The bold array now becomes true, 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 false, 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 true, true, true. Following this, we merge the bold regions by identifying the ranges 0, 3, and 6, 9. Finally, we construct the output string by inserting b at index 0 and /b at index 3, and similarly for the range 6, 9. The resulting string is babc/bxyz-b123/b. This example highlights how the algorithm efficiently handles marking, merging, and constructing the output to produce the desired result. Here, we define a class solution with a method addBoldTag which takes two inputs, the string S and a list of words. The goal is to add bold tags around all substrings in S that match any word in the list. First, we determine the length of the string S and initialize a list called bold with the same length, filled with false. This list will help us track which characters in the string should be bolded. Next, we iterate through each word in the words list. For each word, we use the find method to locate its position in S. If the word is found, we mark the corresponding positions in the bold list as true. We continue searching for subsequent occurrences of the word by updating the start position with find and repeating the process until no more matches are found. Once the bold list is fully populated, we can move on to constructing the final string with the appropriate bold tags. To build the resulting string, we use a list called result to collect the characters and tags. Using a while loop, we iterate through the string s character by character. If the current position is marked as bold, we append the opening bold tag b to the result list and continue appending all consecutive bold characters. Once we reach a non-bold position, we append the closing bold tag /b. If the current position is not bold, we simply append the character as is. This process ensures that the bold tags are correctly placed around all matching substrings. Finally, we use the join method to combine the elements and result into a single string and return it as the output. Here, we start by importing the necessary libraries and defining our solution class with the method addBoldTag, which takes a string s and an array of words as input. The first step is to determine which parts of the input string need to be wrapped with bold tags. To do this, we initialize a Boolean array called bold, where each index corresponds to a character in the string. This array will help us track whether a character should be bolded. Next, we iterate over each word in the array words. For each word, we use the indexOf method to find its starting position in the string s. If the word is found, we mark all the corresponding indices in the bold array as true, indicating that those characters should be bolded. We continue searching for additional occurrences of the word by updating the start index and repeating the process until no more matches are found. This ensures that all instances of the word are accounted for, even if they overlap. Now that we have marked the positions to be bolded, we move on to constructing the resulting string with the bold tags. We use a string builder to efficiently build the output. Starting from the first character, we check if the current index in the bold array is marked as true. If it is, we append the opening bold tag b and then continue appending all consecutive bold characters until we encounter one that is not marked as true. At that point, we append the closing bold tag /b. If the current index is not marked as bold, we simply append the character as is. This process continues until we have processed all characters in the string. Finally, the constructed string is returned as the result, and it contains the original text with appropriate bold tags inserted around the specified substrings. Here, we're working with the input string s equals abc is 123 and the dictionary words equals abc 123. To start, we initialize the length of the string n as 9 and create a Boolean array bold of the same length, where each value is initially set to false. This array will help us track which characters in the string should be bolded. Next, we process each word in the dictionary. For the word ABC, we find its starting position in the string, which is index 0. We then mark the indices 0, 1, and 2 in the bold array as true. Moving to the word 123, we find its starting position at index 6 and mark indices 6, 7, and 8 as true. After processing both words, the bold array becomes true, 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 false, 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 true, 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 indicating the regions that should be bolded in the final output. With the bold array ready, we now construct the resulting string. We initialize an empty list, result, to build the output and start iterating through the string with an index I. At the beginning, bold, 0, is true, so we append the opening bold tag, b, to the result. We then append the bolded characters a, b, and c to the result list. Upon exiting the bold region, we append the closing bold tag, /b. Continuing through the string, the characters x, y, and z are not in a bold region, so they are appended directly. When we reach index 6, bold, 6, is true, so we append another opening bold tag, followed by the bolded characters 1, 2, and 3. Finally, we append the closing bold tag to complete the bold region. The fully constructed string is babc/bxyz_b123/b. In this example, the input string is s equals aap in the dictionary as words equals AAA, ob, bc. We begin by initializing the length of the string n as 7 and the bold array as false, 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 false. For the first word, AAA, we find its starting position at index 0 and mark indices 0, 1, and 2 in the bold array as true. Next, for the word ob, we find its starting position at index 1. This overlaps with the previous marking, so we update the bold array to include index 3 as well, resulting in true, 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 false, false, false. Finally, for the word BC, we find its starting position at index 4 and mark indices 4 and 5 as true, updating the bold array to true, 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 false. This effectively combines overlapping and consecutive matches into one continuous bold region. Now that the bold array is finalized, we construct the resulting string. Starting at index 0, since bold 0 is true, we append the opening bold tag, b, and then include all the bolded characters from index 0 through 5. After exiting the bold region, we append the closing bold tag, /b. The remaining character, c, is appended directly, as it is outside the bolded region. The final output for this example is BAP/B greater than c. In another case, where no words from the dictionary match the input string, such as s equals ABCDF with words equals GH, IJ, no indices are marked as true in the bold array, so the input string is returned unchanged as ABCDF. The algorithm efficiently handles bold regions in the input string by first marking the relevant indices in the bold array and then constructing the final string with HTML tags. It seamlessly manages overlapping and consecutive matches by merging them into a single bold region. For cases where no words from the dictionary exist in the string, the input is returned as is. This approach ensures clarity, correctness, and efficiency, making it a robust solution for the problem. To analyze the time complexity of the solution, we can break it into two main steps. First, there's the process of marking the bold positions in the string. For each word in the given list of words, the algorithm uses s.find to locate all occurrences of that word in the string s. If a word appears multiple times, s.find continues searching from the next position, which can result in O, k*n operations for that word, where k is the number of occurrences and n is the length of s. When we consider all the words in the list, the total time complexity for this marking step becomes O, m*n, where m is the total combined length of all the words in the list. Then, in the second step, after the bold positions are marked, the algorithm iterates through the string to construct the final result with the bold tags. This is a straightforward operation that only requires a single pass over the string, making it O, n. Together, these steps contribute to the overall time complexity of the solution. When we combine the marking and result building steps, the overall time complexity in the worst case is O, m*n, where n is the length of the string s and m is the total length of all the words in the list. However, in the best case, where no words from the list are found in the string, the marking step requires minimal iterations, and the complexity reduces to O, n plus m. Now, turning to space complexity, the primary contributors are the bold array and the result list. The bold array, which tracks which positions in the string are part of a bold section, has a size equal to the length of the string n, so it requires O, n, space. The result list, which holds the final output, can also grow to O, n in size, as it includes the original string and adds bold tags. In a scenario where every character is wrapped in bold tags, the space required for result could scale to approximately 5n, but it is still asymptotically O, n. Since no other significant data structures are used, the total space complexity for the solution remains O, n. Now let's compare this solution to a brute force approach. A naive method might involve checking every possible substring of the string s against the words in the list, leading to O, n squared, comparisons for all substrings, combined with O, m, checks for each word. This would result in a much higher time complexity. In contrast, the current solution avoids such nested substring checks by leveraging the s.find method to directly locate occurrences of words, significantly reducing redundant operations. To summarize, the overall time complexity of this approach is O, m*n, in the worst case, with n as the length of the string and m as the total length of all words in the list. The space complexity is O, n, dominated by the bold array and the result list. By using direct substring searches and a single pass for marking and constructing the result, this solution achieves a much better balance of efficiency compared to a brute force method. When working on this problem, there are a few common mistakes that can trip you up. First, ignoring overlapping matches in the input can lead to incomplete or incorrect bold tags. For example, if one word from the list overlaps with another in the string, you need to merge their intervals to ensure all overlapping characters are included in the bold range. Next, using a naive substring search for every word in the list might seem straightforward, but it can cause significant performance issues for large inputs. Instead, consider optimizing this with a tree, which allows for efficient prefix-based searches. Additionally, pay close attention to indexing. Off by one errors are common when marking bold ranges, such as accidentally skipping the last character of a match or going out of bounds. Another pitfall is hard-coding assumptions, like expecting all words to be unique or lowercase. Always account for edge cases, such as mixed case, duplicates, or even empty strings. Finally, don't overlook edge cases like an empty input string, an empty list of words, or words that are longer than the string. These scenarios can easily lead to runtime errors if not handled properly. Now, let's think about how to approach this problem in an interview setting. One key insight is recognizing patterns involving overlapping intervals. This is a recurring concept in problems like merging intervals, and mastering it can help you tackle a variety of related challenges. Optimization is another critical area to focus on. Demonstrating how to improve a brute force solution, such as using a tree for efficient prefix searches, can impress interviewers. Edge cases are also commonly tested, so make sure to clearly explain how you handle scenarios like empty inputs or overlapping conditions. Beyond implementation, be ready to discuss time and space trade-offs. For instance, using a tree can optimize runtime but comes at the cost of additional memory. Relating this problem to other challenges can also show your depth of understanding. For example, merging intervals in LeetCode 56 uses similar logic to what's required here when combining bold ranges. Building a tree, as seen in LeetCode 208, is directly relevant for optimizing substring searches. Lastly, problems like LeetCode 758, which also involve bold tags, extend these concepts further, making them great resources for practice. There are also alternative approaches you can consider for this problem. One option is using a tree to store the words for efficient prefix-based searches. This significantly reduces the complexity of scanning the string for matches, especially when the list of words is large. The trade-off here is the additional space required to construct the tree. Another approach involves using a two-pointer technique to merge overlapping intervals after identifying the bold ranges. This method is easier to implement but requires pre-processing to determine the intervals first. Finally, there's a brute force approach that uses a hash set to store all the indices that need to be bolded. While this simplifies the merging process, it can be less efficient for larger inputs. Each of these approaches comes with its own trade-offs in terms of simplicity, efficiency, and memory usage, so it's important to choose the one that best fits the constraints of the problem and the requirements of your solution. Great work! We've successfully solved the problem and covered the key concepts. Remember, understanding string manipulation and efficient substring handling is invaluable for technical interviews. Be sure to practice similar problems and subscribe for more coding insights. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!